Welcome to this IB Maths Intense session. Building on what we did in the last video on arithmetic sequences, we're now going to be looking at arithmetic series, which, as we discussed before, is a big topic on the number and algebra section of the course. There it is, arithmetic sequences and series. So something we really need to be able to master. Now, in the earlier video, I showed you how to work with arithmetic sequences, finding particular terms in the sequence using the formula on the formula sheet. But an arithmetic series, as we described earlier, is the sum of a particular part of an arithmetic sequence. So these are the four examples I'd shown you earlier, but this time I've instead of using commas, I've used plus signs to show that they're each an example of an arithmetic series. So 2 plus 4 plus 6 plus 8 plus 10 is the sum of the 5 terms that make up that part of the arithmetic sequence that is the 2 times table. And you will be asked to be able to manipulate or calculate different aspects of arithmetic series. So in each of those examples, we are summing the total of the terms to get an answer. And if you remember, we used sigma notation as a way of denoting that. For example, in that first one, we were finding the sum of the first 5 terms, r equals 1 to 5, of the sequence whose rule was 2r, where r is the number of the term. How do we find a formula for the sum? Well, if we look at that particular series that I just showed you, 5, 8, 11, 14, 17. It's short enough for us to be able to add those up in our head, but I need you to imagine that this goes on for a very long time and you don't want to do that. So let's have a look at what we're actually doing here. Well, here's a little trick. Imagine that I turned the series round the other way and had 17 plus 14 plus 11 plus 8 plus 5. Now something amazing's happened here, because now in each case I've got the same total of 22, and actually what I've got here is 5 lots of 22. Well, let's try and see if that can help us. So I know my sum is going to be 5 lots of 22, and then I'm going to halve that. I hope you can see why I'd halve that, because actually what I've got is the sum of 2 lots of the series here, because I've added one series to the other. So in total I'd end up with 5 times 22 over 2, that's 5 times 11 is 55. We could try and generalize that and think about this in terms of particular parts of the series. So in each case, 22, if you notice, is the sum of the first and the last terms in this series. So what I've done is I've multiplied my first term, u1, which I've added to my last term, which is un, and I've multiplied it by n. In other words, I've multiplied the sum of the first and the last terms by 5, because n's 5 in this case. But then at the end, I halved the result because I'd actually summed the series twice. So that gave me my sum of n terms, was n over 2, u1 plus un. So let's just test that. So that's 5 over 2. First term was 5. The last term in the sequence was 17. And there I get my same 55. And there's one of my formulae for finding the sum of an arithmetic series. Sum of n terms is n over 2 multiplied by the first plus the last term. Now sometimes I might not know straight off what the last term is, but if you remember from our earlier video, we knew that we could calculate un. It's just the first term plus n minus 1d, if you remember that. So we can do a little bit of manipulation here and substitute that into our formula and say, well, another way of looking at it is that s of n equals n over 2 times the first term plus the last term, which is u1 plus n minus 1d. And that can simplify out to give s of n is equal n over 2, 2 times the first term plus n minus 1d. Let's just put a red ring around that as well, because there is our second version of the same formula. They're not different, they're just two ways of looking at the same thing. If you happen to know the last term, you can plug it into the first formula. If you don't, you can work it out on the fly by using the formula that we've just derived using 2u1 plus n minus 1d inside the brackets. Those are our two formulae, and we can use whichever one fits the case that we've been given. And indeed, here they are. They're on our formula sheet. The sum of n terms of an arithmetic sequence, both versions are given using the notation that we just used. And this is great. It gives us a lot of power to be able to do fairly complex calculations. So for example, if I had the sum of the first numbers, I've got the numbers 1 to 100. If you asked me to add those up in my head, that would take me a while. But if I wanted the sum of the first 100 numbers, well, that's easy. I'm just going to use n over 2, which is 100 over 2, which is 50, multiplied by, well, I know the first and the last terms, 1 plus 100. So 50 times 101, which is 5050. That didn't take long. It was a lot quicker than adding them all up in my head or using the calculator. So a very, very powerful formula, I'm sure you'll agree. Let's have a look at some of the types of questions that will be expected to answer using these formula, because it won't always just be a case of find the sum. It will be in some cases, but there will be complications. So here's an easy question. Find the sum of the first 50 terms of an arithmetic series with first term 10 and a common difference of 2. Now, my advice in any of these questions is to write down, to start with, what you know. So u1, the first term is 10. The common difference, d, is equal to 2. And we want the first 50 terms, so we're talking about n equals 50. So now it's a case of which of my formulae here is going to be the best to use. Well, we haven't been given the last term. So in this case, I'm just going to go with the longer formula here, and I can say S50, sum of the first 50 terms, is n over 2, that's 25, because 50 divided by 2 is 25. 2 lots of the first term, that's 20, plus, and then n minus 1, 50 minus 1 is 49, times 2, which is the common difference. And if I work that all out on my calculator, I've got 25 times 118, because 49 times 2 is 108, is 98, plus 20 gives me 118. 25 times 118 is 2,950. No problem. Nice and straightforward, but I was given lots of information there, so I could just plug that straight into the formula. Second question, a little bit more difficult and requires you to do a little bit more work before you can start. It says find the sum of all the multiples of 8 between 60 and 20. So we need to work a little bit harder to write down what we know. So the first term of this series is the first multiple of 8 after 60, which if you know your 8 times table, hopefully you know is 64. And the last term, well, we need to work from 200. And does 200 divide by 8? Well, actually, fortunately, it does. If you divide 200 by 8, you'll get 25. So we know that our last term, un, equals 200. But we don't know how many terms there are. We don't know n. But we do know the common difference is equal to 8, because multiples of 8 go up in 8. So I can't yet use either of the two formulas because I need to find n. So the easiest way to find n is to see if we can find which term in a sequence that starts at 64 and ends in 200 with a common difference of 8, which term is the term 200. So the first thing I'll do is I'll work backwards from my earlier formula that we learnt in the last video for the nth term. So I know that 200 was equal to the first term, 64, plus n minus 1 times the common difference, which is 8. So if I expand all of that out, I get 200, let's just do this quickly, 64 plus 8n minus 8, 200 equals 56 plus 8n. Let's switch that over. That means 8n must equal 144. So n is equal to 18. There are 18 terms in this series. Now I can go straight into, well, whichever one of the formula I like. But I've got enough. I know the first term and the last term, so I could just go for this one, which is the easiest. So the sum of my 18 terms is equal to 18 over 2, which is 9. Multiplied by the first plus the last. Well, the first was 64 and the last was 200. So 9 times 264 is equal to 2,376. Now, that was a little bit trickier because I had to find the missing information. I couldn't use the sum formulae without finding out the value of n. And to find out n, I had to work backwards using the original formula from the last video for the nth term. In this question, again, not quite so straightforward because I haven't got everything I need to know. So first term is 20. Let's write down what we know. U1 is equal to 20. The common difference is 6. If the sum of all the terms is 3210, how many terms are there? So what do we know here? We know that the sum of my n terms is 3,210, and I want to find n. So I'm going to need to go to one of my formulae and work backwards. So let's go with the first one because I don't know the last term. So I'm going to use this one here, and I'm just going to write in what I know. 3,210 is equal to n over 2. I'm trying to find n, so I don't know what it is. 2 times the first term, which is 40, plus, and then my common difference, d, is 6. 6 lots of n minus 1. And I've just got actually this will end up being a quadratic, if you can see, because I'm going to be multiplying n by n. So if I multiply everything by 2 to get rid of that fraction, 6,420 equals n times 40 plus 6n minus 6. That will give me 6420 equals 6n squared plus 34n. Nice quadratic has just come out here. Let's rearrange that. 6n squared minus plus 34n minus 6,420 equals 0. I can just halve everything there to make the numbers a bit simpler. The 3n squared plus 17n minus 3,210 equals 0. Now, my my ability with double brackets is not brilliant here, so I'm just going to use the quadratic formula. So let's go back up here, and hopefully you can remember how the quadratic formula works. So my value of n here is going to be minus b, so b here is 17, minus 17, plus or minus the square root of b squared, well that's 17 squared, minus 4, a is 3, and c is minus 3,210, all over 2a, which is 6. That's on the formula sheet as prior knowledge. Hopefully it's fairly well embedded in your heads anyway from your earlier maths. That's equal to minus 17 plus or minus. Let's work out everything there. 17 squared minus 4 times 3 times minus 3,210. That's going to be a positive. Work that out on the calculator. That comes to 38,809 and divided by 6. Now, I will have two results here, but one of them is going to be positive and one of them is going to be negative. So I can forget about the negative answer because we can't have a negative value for the number of terms, n. So I'm just going to go with n is equal to minus 17 plus root 38,809 over 6, which is equal to 30. If I work that through on my calculator. Brilliant. So that was a little bit more long-winded, and we were tested on a number of things there. Solving a quadratic ended up in that particular problem. But that's very common when we're working with these formulae. It won't just be necessarily a straightforward calculation. Two more examples and then I think we've done arithmetic series. This one again is an example like in the earlier video where we will have to solve some sort of simultaneous equations to find a result. We're given information but not enough to be able to solve in one go. So we're told that the second term of a sequence is 10. Let's just write down what we know. We know that U2, not Bono, but U2, the second term of the sequence, is 10. The sum of the first 5 terms, S5, is equal to 110. And that's all. Nothing else. And we need to find the first term, which we're calling A, and the common difference D. So a bit of thinking, and we're going to need to use both formulae here to be able to work this out. So the first thing is that I know that my second term, 10, was the sum of A and D. So 10 was my first term plus the difference gave me my second term, 10. So there we are. That's the first thing that I know. A plus D equals 10. The second thing I know is that 110, the sum, was equal to n over 2, which is 5 over 2, because we know it's the sum of the first 5 terms. 2 times the first term, 2a, plus n minus 1, that's 4 times the common difference, 2a plus 4d. And if I work with that, I can multiply by 2. 220 equals 10a plus 20d. I can simplify that by dividing by 10. 22 equals a plus 2d. Now if I return over to the other side and write that equation down, a plus 2d equals 22, you'll see I've got a nice pair of simultaneous equations, and actually they solve quite simply. If I subtract the first one from the second one, the a's disappear, 2d minus d is d, and 22 minus 10 is 12. So our common difference is 12. We've worked that out, and now I need to find out the value of a. Well, we know from the first equation that a plus d is equal to 10. So a plus 12 equals 10. So that means a must be equal to negative 2. So I've got a sequence here that goes minus 2 and then goes up by 12, goes to 10 and then 22 and so on. And if I add those up, the first 5 terms of that sequence, no doubt I'll find that the sum is 110. But that was an example of a nice straightforward simultaneous equation that comes into play. Don't be surprised if you find one of those. And then lastly, here is a very normal kind of question. We're not finding an exact answer. We want to find the least number of terms here for this series, minus 5 plus 1 plus 7 plus 13. The least number of terms so that the sum is greater than 500. So we want the sum of n terms to be greater than 500. We know that the first term, u1, is equal to minus 5. Notice that I'm writing down what I know for every one of these questions, just so I've got it in front of me and I don't make any mistakes. So I'm going to use this formula here because I don't have the last term and I don't have a value for n, but I can substitute everything else in there apart from n. So if I say that we want the sum to equal 500, then I would get n over 2 and then 2 lots of the first term, minus 10, plus n minus 1 times the difference, which is 6. And if I work that through, multiply by 2 to get 1,000 equals minus 10n plus 6n squared minus 6n. So I end up with 6n squared minus 16n minus 1,000 equals 0. It's a quadratic, and I can halve everything again there to make the maths a little bit easier. 3n squared minus 8n minus 500 equals 0. That's just rearranging everything to create a quadratic. And then we're back where we were before. and we can use the quadratic formula here to work out a value for n. So n is equal to minus b, which is minus 6, minus 8, plus or minus square root of b squared, which is 8 squared, minus 4, a is 3, and c is minus 500, all square rooted all over 2a, which is 6. So if I work that through, it's negative. It's minus 8. It's not minus 8. It's plus 8 because it's minus b, and minus is plus. So let's just correct myself there. It's not a minus. Apologies. And again, there it's not minus. It's plus. It's 8 plus or minus the square root of 6,064. If we work that out in our calculator, all divided by 6. And if you work that out, you will find that gives two answers. We're not interested in the negative answer here because we can't have a negative number of terms. So we will end up with 8 plus root 6,064, all divided by 6, which comes to approximately 14.31. Now we can't have 14.31 terms, but we know that if the term is the 14th term, the total won't quite yet be 500. And we know that the 15th term, the total will be greater than 500. So the answer of our question here is n must be equal to 15 for the sum of n terms to be greater than 500. So there we go. There's a number of different flavours of questions, and I can't claim hand on heart that I've covered every different eventuality, but I've tried to show you that you need to use your imagination and be able to manipulate the formulae and use a number of other techniques like the quadratic formula, like simultaneous equations, to be able to work backwards to find your required result. You won't always be being asked to find the sum. You might be using your knowledge of the sum to work backwards to find any of the other components of those formulae at the top of this page. So thank you so much for watching. We will go forward and build on what we've done and start looking at geometric sequences and series in the next 2 videos. Don't forget to like this video, subscribe to my YouTube channel, IB Maths Intense, tell your friends I'm here, and drop me an email on ibmathsintense@gmail.com if you've got any comments, any requests, or if you've spotted any mistakes that I may have made. In the meantime, enjoy your maths and take care.